In this lecture, we're going to turn to the basic properties of stars: stellar distances and brightnesses, colors, and luminosities. Finding distances in astronomy is one of the most difficult and most fundamental of measurements that we can make. The reason that makes it difficult is that you often cannot use the same techniques for every object. Instead, astronomers use a distance ladder. For example, this photograph here shows some enormous scale that can be represented in an astronomical scene. Comet Pan-STARRS is a comet crossing through the inner solar system. Most of the stars that you see in this picture are in the Milky Way galaxy, and this tiny fuzzball out here, the elliptical shape with little dark spots, splotches in it, and this fuzzball next to it, is the nearest large galaxy to our own, the Andromeda Galaxy, more than 1 million light-years away. The methods we would use to measure the distance to Comet Pan-STARRS is not the same as we would use to estimate the distances to the stars in this field. And indeed, different stars might require different methods still, and measuring the distance to Andromeda requires other methods altogether. However, what a distance ladder allows us to do is to start out close by, calibrate a nearby measurement, and then use that to step out to the next distance. So we start in the solar system, reach out to the nearest stars, then use properties of those nearest stars to reach out to similar stars at greater distance, and so on and so forth, slowly working your way outwards like a person climbing up a ladder step by step. We're going to be talking a lot about distances in this class. Today I don't want to cover the entire astronomical distance ladder to the edge of the universe, but only those portions that are most relevant to the discussion of the properties of stars. The first rung of the distance ladder is to measure distances inside the solar system using radar. The way this works is you bounce radio pulses off a planet. For example, if I wanted to know the distance of Mars, I would point my radio telescope at Mars and ping it with a radar signal. I would measure the round-trip travel time, how long it takes the signal to go out and come back, divide that by 2, that gives me the one-way travel time. Since radio waves are light waves moving at the speed of light, the distance is simply given by the one-way travel time multiplied by the speed of light. This is a very straightforward and very accurate way to measure distances inside the solar system. And indeed, distances inside the solar system are known to very high precision. So much so that we use the average distance between the Earth and the Sun as the standard unit of distance in astronomy. It becomes our fundamental yardstick, and we call it the astronomical unit. Using radar methods and reducing them to metric units, the astronomical unit has been adopted to be 149,597,870.7 kilometers. Of course, as we've learned before, the Earth is not on a circular orbit at the same distance from the Sun, but is on a slightly elliptical orbit. So while this distance represents kind of an average distance between the Earth and the Sun, it's not actually measured in terms of the Earth-Sun distance anymore, but rather it's calibrated in terms of an ensemble of planetary distances and related to the mean distance of the Earth from the Sun. The distance from the Earth to the Sun changes all the time, and so we adopt a formal definition of the unit to be as our working yardstick. This is very common, and you'll encounter it in all systems of measurements. Now that we have the average distance of the Earth from the Sun, how do we use that to measure other distances? For that, we're going to use geometry in the form of parallaxes. You may remember parallaxes from the previous unit when we talked about the work of Copernicus and how the fact that the Earth orbiting around the Sun should cause the position of a nearby star to shift relative to background stars as you look at the star from January to July going over the course of a single orbit. In July, the star will appear against these background stars on the left-hand side of this grouping of stars, whereas in January, we've shifted to 2 astronomical units away, and now we would see this nearby star against this pattern of 5 stars as part of this constellation. We call this effect parallax. If you look carefully at this diagram here on the left, you can see that we geometrically can describe a triangle. The first leg of the triangle joins the line going from the sun to the nearby star back to the Earth at one position, and we describe the angle that's formed here, P, to be the parallax angle. We close the triangle with 1 astronomical unit, the distance of the sun from the Earth. And D, of course, is the distance of the sun to the star. Now, we know that the stars are very far away. Indeed, D is much, much bigger than 1 astronomical unit, and so this is a very, very long, thin triangle. But it's a triangle nonetheless, and geometry tells us if you know one angle and one side of a right triangle, in which a right angle here is the Earth-Sun-star distance, forms this right angle, then I know all of the other angles and the sides just by applying trigonometry. This is very important. This gives us a way to use our knowledge of the size of the Earth's orbit as a yardstick to geometrically measure the distances to nearby stars using what we call trigonometric parallaxes. The parallax works as follows. The parallax of a star is inversely proportional to its distance. Very, very close stars make small triangles with big parallax angles, and therefore their parallaxes are easy to see. A more distant star has a smaller parallax angle. But the important thing is, if the object is 2.5 times further away, for example, its parallax angle will be exactly 2.5 times smaller. The parallax of a star is inversely proportional to its distance by the first power. Star is 10 times further away, it's a 10 times smaller parallax. Furthermore, you'll notice how these triangles are getting long and thin. I've had to greatly exaggerate how close the stars are to the solar system to make these triangles even possible to draw on the screen. In reality, the parallax angle is tiny. The largest parallax is only 3/4 of an arc second. That's less than more than 4,000 times less, 1/4000th of 1 degree. That's a tiny angle, and indeed, it wasn't until 1835 that our telescope technology developed to the point that the first parallaxes were able to be observed. The small angle approximation that we can use, however, is of great utility because it allows us to simplify the trigonometry. In fact, we can sweep it under the rug altogether. Let's go back to our picture of this parallax triangle. We have a nearby star with background stars. We form this triangle here from the sun, the star, and the Earth. 1 astronomical unit between the Earth and the sun, and D is the distance of the sun to the nearby star. P is the parallax angle. In the small angle approximation, the distance D is 1 over the parallax angle. If I measure the parallax angle in units of arc seconds, an arc second is 1/3600th of a degree, then the distance to that star will be 1 parsec. A parsec is a funny word. It's a portmanteau word. It's a mashup of two words. A parsec is the distance of which a star has a parallax of 1 arc second. So a 1 parallax second is a parsec. The parsec is going to be the fundamental unit we use because it is directly relatable to two fundamental observables: the parallax angle of the star measured in arc seconds, and is calibrated in terms of 1 astronomical unit, the distance of the Earth from the sun. If I now show what a parsec is in those units, a parsec is 206,265 astronomical units, which translates into 3.26 light years, a light year being the distance that light travels through a vacuum in 1 year. The parsec is going to be a lot more useful to us in light years, but I'll occasionally bring the light year into play, if only because conceptually we all have think we have an idea at least of how big a light year is. It's how far light travels in a year. A parsec, 206,265 AUs? Not so much. So I'm going to switch back and forth between these units as a convenience, but bear in mind that professional astronomers like myself will use the parsec because it's closely tied to the actual observables. Let's see an example of how we use the parallax to compute a distance. The closest star to the Earth, other than the Sun, is Proxima Centauri, a very dim red dwarf star in the constellation of Centaurus. If you were down in the southern hemisphere, say in Australia or New Zealand or South Africa, you would see two fairly bright stars up in the sky during certain times of the year, Alpha and Beta Centauri. Alpha and Beta Centauri are very useful because they point to the Southern Cross. What you would not see is the nearest by star, this little teeny tiny red star that's barely distinguishable among all these other thousands upon thousands of stars in this image. Here's a zoom up. It barely fills a couple pixels, but you'll notice it's a dim red star. This is Proxima Centauri. It's not visible to the naked eye, but it is visible in photographic telescope techniques. The parallax of Proxima Centauri is 0.769 arcseconds. If we use our parallax formula, d is equal to 1 over p, and put in 0.769 arcseconds for p, do the math, works out that the distance to Proxima Centauri is 1.3 parsecs. Translating that into our preferred units of light years and astronomical units, Proxima Centauri is 4.24 light years away, or 268,140 astronomical units. Put another way, Proxima Centauri is so far away that light takes 4¼ years to reach us from its surface, and to put it in scale of our solar system, Proxima Centauri is a little over 268,000 times further away from the Sun as the Earth. This gives you, and this is only the nearest by star. This is a map made by the RECONS project at Georgia State University, showing, at least to date, all of the stars known to be within 10 parsecs of the Sun, approximately within 32.6 light years. If you look carefully at this diagram, you'll notice that all of these stars are red. That's because most of the stars around us are dim little red dwarfs. You'll see a few occasional yellow stars going by, a couple blue and whitish stars. The color representations are not true colors, but attempting to give us some idea of the many different types of stars nearby. We see stars of all different colors. If you're lucky enough to have a high-definition monitor, you may notice that a number of these stars are accompanied by a little number, like a 2, or a 3, or sometimes even a 4 or a 5. This is the multiplicity of the system. Many stars are actually double stars. For example, the nearest star system to our own, Proxima Centauri, we're here at the Sun. This is now the Proxima Centauri system, but it's been collapsed down, so you can't see Alpha 1 and Alpha 2 Centauri, which Centauri A is in fact a Sun-like star. There are 3 systems. The Alpha Centauri system is a triple star system. If you look closely, you'll notice some stars, like this one right here near my cursor, says 2P, 2P, 9P. That should be a hint. Those are stars that are known to have exoplanet systems. We haven't completed an exoplanet census of all the stars even within 10 parsecs of us, but at the time this plot was made, this shows you the number of planetary systems other than our own. You also get another interesting clue. The people who made this diagram labeled the Sun as 9P. They clearly are people who think Pluto is still a planet. Maybe one of these days they'll correct it and call it 8P. The problem with parallaxes is the further the star is away from us, the smaller the parallax is. The smaller the parallax is, the harder it is to measure it. Eventually, our technology hits a limit, and we can't measure angles below a certain size. To be able to get around this problem, astronomers have developed a series of increasingly sensitive satellites that get above the blurring effects of the Earth's atmosphere and try to measure parallaxes to the smallest angles possible. The first of these satellites devoted to measuring parallax was the Hipparcos satellite, launched in 1989 by the European Space Agency. The Hipparcos satellite was designed to measure parallaxes down to 1/1000th of an arcsecond. 1/1000th of an arcsecond is able to give you a distance good to about a 10% precision out to about 100 parsecs. But the limit is about 1,000 parsecs. If you measure a parallax of 1/1000th of an arcsecond, 1/1/1000th is 1,000 parsecs. However, that's at the limits of the spacecraft. You can get about a 10% distance for about 10 times larger, or 0.01 arcseconds, 1 over 0.01 is 100 parsecs. That may not sound like much, but there's a lot of stars in the Milky Way, more than 200 billion. And so even if you only measure distances out to about 100 parsecs, you're still measuring approximately 100,000 stars out of the 200 billion in our galaxy. The Hipparcos satellite represented a major advance in our ability to measure the distances of stars, which is extremely important for being able to understand their physical properties. But it's barely out of the local solar neighborhood. As a consequence, a new European Space Agency mission named Gaia was launched in 2013 that tries to go even further. Gaia was designed to measure parallaxes down to 10 microarcseconds, 10 millionths of an arcsecond. This gives you distances good to a 10% precision out to 10,000 parsecs for over 200 million stars. In this artist's rendition of the shape of the Milky Way, we see the Hipparcos limit of approximately 1,000 parsecs. The Gaia limit is getting out to more than 10,000 parsecs. Since the center of our Milky Way is 8,000 parsecs away, this encompasses an enormous sector of our galaxy. The primary science mission of Gaia began in July of 2014, and the first results are not expected to be published for about a year and a half, or sometime in the middle of 2006. Early 2015, early 2016 for the first data release. The spacecraft has a multi-year mission which will only give us multiple measurements and will help us increase the precision of the parallaxes measured. It's hoped over time that while 10% parallaxes will be able to be measured for 200 million stars, they will be able to measure parallaxes of slightly less precision, but those precisions can get greater as they make multiple measurements. The hope is the spacecraft will last long enough to approach nearly 1 billion stars in the Milky Way with good precision distances. Even 1 billion is only a fraction of a percent of the more than 200 billion stars in our Milky Way. Nonetheless, it's going to give us an enormously improved view of the architecture of our part of the galaxy. What do we do with these distances? That's part of the subject of the next part of this lecture.